All right, welcome to Chapter 7, Part 6. This should be the last part. Might be a little bit long, but we are going to talk about other substrates. So we've been looking at substitution and elimination using an alkyl halide where the halogen is the leaving group, right? The RX, and then we have either a nucleophile or a base, and we get a product, right? Either where we have substituted the nucleophile for the halogen or where we eliminate the halogen and make an alkene. Now, halogens aren't the only good leaving groups. There's a variety of other leaving groups. You see pictured here on the slide 3 such examples. You have the mesylate, the tosylate, and the triflate groups. What we're going to focus on is the tosylate. Something you might notice, though, they're all sort of sulfonate derivatives. And what is notable about them, so for instance, if we look at that OTS group, once it leaves, right, and that arrow should be coming from that bond, you wind up with this leaving group. Now, halogens are good leaving groups because they are stable, right? They're stable once they leave and they can hold that charge. Can you see why this leaving group might be able to really stabilize that charge? There are lots of different resonance structures. That negative charge is shared over many atoms in this leaving group. So this is actually a really great leaving group. Again, it's one of several: mesylate, tosylate, triflate here. There are also others, but we're going to focus on that OTS group. One of the nice things about the OTS group is they're very easy to make from alcohols. So if we look at an alcohol itself is not a very good leaving group. If you think about what would be left if the alcohol was kicked out, it would be hydroxide. And hydroxide is one of our strong bases, right? So if it's a strong base, that means it's reactive. That means that charge is not stabilized. You see that negative charge is localized on that oxygen alone in comparison to on that tosylate where it is shared over many atoms. So an alcohol is not a good leaving group, but an alcohol is an interesting substrate because it can easily be turned into a good leaving group. So we're going to make into a better leaving group. We are going to see in this last video, in this last section of Chapter 7, how we can start with alcohols and do substitution and elimination reactions if we just alter the alcohol a little bit. So one reaction I want you to know, and you do not need to know the mechanism for this reaction, is just if you take an alcohol and you treat with tosyl chloride, and so you can just abbreviate it, TSCl, and you should know that abbreviation right here. That's tosyl chloride. If you treat an alcohol with tosyl chloride and a little bit of pyridine is, it's a base. It's used to pick up a proton from the alcohol. Again, you don't need to know this mechanism, but it will transform your alcohol into an OTS group, into a tosylate group. So you don't need to know the mechanism, but you do need to know this reaction. You need to be able to predict the products. You need to be able to utilize the reagents. All right, you need to recognize tosyl chloride and pyridine. Now, pyridine is often abbreviated just PY. So if you see TSCl, tosyl chloride, and pyridine, it is simply going to replace an alcohol with an OTS group. It does not change the oxygen from the alcohol is still there, so you do not change the configuration. Notice it's, S stays S. What this does is allows us to have a starting material that is comparable to your alkyl halide. So this can now undergo substitution or elimination in exactly the same way an alkyl halide would. So you can use a strong base, strong nucleophile, weak base, weak nucleophile, and you predict products using, predict products using the charts that we have established previously in this chapter. So, for instance, if you treat this primary tosylate with sodium hydroxide, and sodium hydroxide is a strong base, strong nucleophile, you are going to have E2 and SN2. Now, based on our charts, I would give you a solvent to help you decide if this was going to be elimination or substitution, right? So let's say this was done in DMSO. Then you would get that major product of a substitution. Now, I don't know why you would tosylate and then make an alcohol, but you can do it if you want to. If we have that secondary tosylate, now again, I would like you to use solvent to differentiate. So for one like this, I would have a protic solvent under the arrow. So you would have your strong base, strong nucleophile, your protic solvent, your secondary leaving group, and you would get an elimination, right? So these behave like alkyl halides once you have that tosylate. There is a way to utilize this to make Zaitsev and Hoffman products, right? If you wanted to use control there, you would just use a bulky base versus a smaller base, right? So it gives you a lot of control. Another way that you can utilize alcohols to do substitution and elimination reactions is to use, So you can start with your alcohol, and instead of using a tosylate, you can use a strong acid. So we are going to use HX. Now this could be HBr or HCl. Primarily, those are the ones you're going to see. You may see HI, but one of these strong acids, and you'll actually see that this leads to a substitution where you can replace the OH with the halogen. So let's actually explore the mechanism of why that works. So let's take our substitution with an acid, and let's look at the mechanism. So you're going to start with your alcohol. This is not a good leaving group, right? You are not going to just be able to use like sodium bromide and switch the OH out with the bromine. But when you use HBr, what happens first is a proton transfer. You get a proton transferred to the alcohol, and think about what that means. Now, instead of hydroxide, you have water, and water is a fantastic leaving group because water is super stable once it's gone. So then, now we have that bromide ion, which is a strong nucleophile, weak base, so it's not going to eliminate, but it's a strong nucleophile. All that electron density is going to be attracted to that carbon, that electrophilic carbon is even more electron poor once the oxygen next door has a plus charge, right? If oxygen is already pulling electron density away, think about how much harder it's going to pull electron density when the oxygen itself is electron poor. So we get our nucleophilic attack and loss of leaving group. This is an SN2 mechanism, right? It's concerted. The nucleophile is attacking, the leaving group is leaving all at once. The only difference was we had to make the leaving group better in a sort of a prequel, a previous step. So then we get our bromine, plus we've lost some water, right? So we have a substitution. It goes by an SN2 mechanism because this was a primary alcohol. So it is a primary substrate here. We have a strong nucleophile. When we have a strong nucleophile, weak base, and a primary substrate, you can look at your chart. That is going to lead to an SN2 reaction. So will it always be an SN2 reaction? Well, no. If you think about your strong nucleophiles that are weak bases, they're SN2 unless it's tertiary. So the example that we see over here, and we'll just use a really specific small example here. Let's say we're using HCl. We're still going to replace that alcohol with the chlorine. We're still going to get a substitution, but the mechanism is going to be a little bit different, right? So we still have to protonate, right? The alcohol is not a good leaving group, so we still have to protonate first. We make water, which is a great leaving group, but we have chloride ions around now, but the chloride can't get to that tertiary carbon. No SN2 on tertiary substrates, right? That's one of the rules we learned in like part 2 of this chapter. So we get an SN1 mechanism where the leaving group leaves first, and we make a pretty stable tertiary carbocation. Well, now that it is not sterically hindered anymore, the chloride can attack. We can get that nucleophilic attack, and we get our substitution. So it's the same rules that applied when we had a halogen. Literally the only difference is the first step. We just need to make the leaving group better. Right, so we are going to have alcohols treated with HX, giving us alkyl halides, right, in substitution, either SN2 or SN1, depending on if we're dealing with a primary, secondary, or tertiary alcohol. We can also eliminate alcohols. We can do elimination reactions with alcohols in acidic conditions without using a tosylate intermediate if we change up our acid. So now we want to do an elimination of an alcohol. And to do this, we are going to take an alcohol and treat it with H2SO4, so concentrated sulfuric acid. You're also going to see heat, but concentrate mainly on the acid. The temperature may or may not be referenced. And you're going to make an alkene. Now, how does this work? So the same mechanism that we've seen so far, we know our alcohol, and we'll go with the example that they've shown over here. We know that OH is not a good leaving group. So if we have a strong acid around, we are going to protonate to make a better leaving group. Now, in this case, we've just made, OH2. We've made our great leaving group of water. It's a tertiary alcohol. So this will leave on its own. The difference between H2SO4 and HX is the HSO4, right, byproduct that you get here is not a good nucleophile. It's bulky. It is not going to attack. It does not have as much localized charge as a bromine or chlorine ion. It is not a nucleophile. So, not a good nucleophile. So instead of getting a nucleophilic attack, we're going to get a base reaction. We're going to get an elimination. So what is going to act as our base? HSO4 is still the conjugate base of a very strong acid, so it's not really going to act as a base for us. But what is around even in the most concentrated H2SO4? Even in your most concentrated acids, it's still a solution in water. It's just the most concentrated solution it can be. And so water is around, and water can act as a base. And so water will pick up the beta proton and make your double bond. So when you use H2SO4, you don't get a substitution because you don't have that nucleophile, but you do get an elimination. And this goes by, what we looked at here, that E1 mechanism. And a lot of that has to do with if you're going to make a stable carbocation or not. I want to look at one other thing here. If you do have a choice, so if you're predicting products, let's say we have this alcohol. If we treat this with concentrated H2SO4, there are different beta protons that will lead to different products. The major product for this type of elimination will be Zaitsev. Right? It will give you, because water is going to be a small base, so it will give you the more stable, more substituted double bond. Right? So let's just review. You can eliminate an alcohol to give the Zaitsev product if you wanted to give the Hoffman product. You couldn't use H2SO4, but you could take what we've learned in this video and you could make a tosylate, so tosyl chloride and pyridine. That's going to turn that into OTS. And now that's just like any other leaving group, any of your halogen leaving groups. And how could you get a Hoffman product? You could treat it with a bulky base, potassium tertbutoxide, for instance. And now you could get the Hoffman product. So you've learned four reactions here, right? You've learned how to tosylate. You're going to take an alcohol and make it into a tosyl group and just use tosyl chloride and pyridine. You have learned how to substitute an alcohol using HX. You've learned how to eliminate an alcohol using H2SO4, right? And that's going to make an alkene. And then you can utilize these reactions to do various substitutions and eliminations. So you have a lot of synthetic power now. What we are aiming to do in this class is learn all of these different tools, because what we are going to get into by the time we get to Unit 4 and then throughout Organic 2 is taking all these reactions that we've learned and starting to put them together to make more interesting organic molecules. So you definitely want to take the time to learn these reactions now, because we will keep using them. Now, Klein loves a nice summary slide. He makes a lot of good summary charts in the book as well. You can start with an alkyl halide, right? You can make an alcohol. You can make an alkene in a lot of different ways. You can make other functional groups because you can use different nucleophiles, right? If you use an alkoxide, you can make an ether. You can make thiols. You can make nitriles. You can even make esters if you use these acetate or these carboxylate ions. You can take your alcohols and you can make alkyl halides, tosylates. You can loop back around and get to alkenes. You could use H2SO4 to get to an alkene, right? There's a lot of options now, and we're going to keep building on that. Here you have another summary slide. This goes over a lot of what we covered in this video of how you can get between alcohols, alkyl halides, tosylates, and alkenes, and back. Now, when we get to, and then even gets into Zaitsev versus Hoffman. So this is a great summary slide of this particular video. So this would be good to have on hand while you're practicing. And you can, these are the reactions that you're going to be needing to commit to memory. One of the things that we're going to build on in chapter 8, when we get into unit 3, is what can we do with an alkene, right? So we're going to learn how to start with alkyl halides, make alkenes, from alkenes make other functional groups, right? So we're just going to keep building off of what we learn in this in this class. Okay, so before I get to that slide, it's one of the reasons it's very hard for me to answer the question, is the test going to be cumulative? Is it going to focus on the new material? Each test focuses on the new material, but builds off of the old material. So there will always be old material on exams. One thing that you may see in practice tests and practice problems is alkene nomenclature. I wanted to make a note on this right now. We will do alkene nomenclature in chapter 8. We will cover that in unit 3. I will go back and hit E and Z if you've come across that and you're wondering why I haven't talked about it yet. I cover that when I actually talk about naming alkenes. We will do that on unit 3. I will not ask you any alkene naming questions on test 2. Synthetic strategies and retrosynthesis. We are going to cover this in chapter 11. You don't need to worry too much about retrosynthetic analysis right now. We will start to approach that in chapter 8 and 9, and then we will spend a lot of time on it in chapter 11. So I'm just going to breeze by this. Right now, what you need to pay attention to, and we've already talked about solvent effects. Okay, what you need to pay attention to, the type of problems you're going to see would be, I give you a starting material, I give you a reagent. Can you predict the product? That is going to be one thing that we've really focused on. There will be a smaller number of problems where I may give you a starting material and a product, and I ask you to fill in the blank. Eventually, you will be able to fill in any of the missing pieces of starting material, reagent, or product. The majority in Unit 2, though, will follow this model. I give you starting material and the reagent conditions, and you give me the product. Lots of practice. I always recommend this. Write down your questions, send me emails, send me group me messages, come see me in office hours. I'll see you in chapter 8.